Hello, everyone, and welcome to the launch of the Handbook on Soft Robotics. It's great to see you all. My name is Barry Mulvey. I'm a final year PhD student here in Imperial College London, and it's my privilege to act as MC for this evening's event. Thank you very much for joining us. A bit of housekeeping before we get started. So for those in person, if a fire alarm sounds at any stage, please leave through one of the exits immediately, follow the evacuation signs, and proceed to the fire assembly points outside the building. I'd also ask that you please mute your mobile phones, and for those joining us online, if you could please mute your microphones for now. This evening promises to be a fascinating journey into the world of soft robotics. We're really excited to be launching the world's first handbook on soft robotics, which has recently been published by Springer Nature. And there are multiple dimensions to this handbook. The depth of coverage reflects the extraordinary collaboration of a community of co-authors from around the globe working on soft robotics. And by way of acknowledgement to the authors, they are Cecilia Laschi, National University of Singapore, Barbara Mazzoli from the Italian Institute of Technology, Thrishantha Nanayakkara, Barry Mulvey, Shahara Pereira, Yukun Ge, Shenwei Yu, and Parvati Sunil Kumar, Imperial College London, Izuru Gadage from Texas A&M University, Hunter Gilbert from Louisiana State University, Christian Duriez from INRIA in Lille, Shinichi Hirai from Mitsumaikan, Angus Clark, Shinran Wang, and Alex Ran from Imperial, Nicholas Rojas from the Boston Dynamics Robotics and AI Institute, Manu Srivastava from Clemson, Ian Walker from University of Wyoming, Cynthia Sung from University of Pennsylvania, Jamie Pike from EPFL, and Fumiya Ida from the University of Cambridge. And the handbook is the brainchild of its editor, Professor Thrishantha Nanayakkara. The breadth of topics and expert contributions speaks to the regard in which Thrish is held, his powers of persuasion, perhaps, and suggests that he needs little introduction. But for those who might be less familiar with soft robotics here, and you're particularly welcome, Thrish is Professor of Robotics and Director of the Morph Lab in the Dyson School of Design Engineering here in Imperial College London. And his interests span from using soft robots to test hypotheses for embodied intelligence. In terms of this evening's proceedings, Professor Fumiya Ida from the University of Cambridge will provide an introduction to the soft robotics community, and the authors will then give an overview of each chapter. And then this will be followed by a discussion with the authors and an audience Q&A. So at this point, yeah, I just want to thank you again for being here. It's fantastic to see so many people here in person and also those online. We've had hundreds of registrations, so we're really excited. So yeah, to begin, Fumiya Ida is hopefully online, Professor of Robotics in the Department of Engineering at the University of Cambridge, where he leads the Bio-Inspired Robotics Lab, and it's my pleasure to hand over to him now. Thank you.
Okay, thank you very much, Barry. I hope you can hear me very okay. So my name is Fumiya Ida. Okay, well, anyhow, I think I can start. Okay, now I see it. Thank you. Yeah, so, well, first of all, I'd like to send you many congratulations to Thrish and all other contributors for this handbook, Soft Robotics. I think this is going to be a very important milestone in your community, and I'm very, very happy to see this huge impact in this community. So just want to give you a brief introduction, a brief history of soft robotics. The soft robotics is something very, very important for my own career. And I am very happy to start this 2010 small seminar on soft robotics, Swiss Japan soft robotics. And that time I didn't imagine that this community could go this far. But the important milestone for our community was the 2013 International Workshop on Soft Robotics we had in Switzerland, Ascona. That time we had officially many important figures in this community joined together to discuss what's important in this field. And ever since, this community grow only bigger and bigger. And of course, another important milestone, the 2018 International Conference on RoboSoft started in Italy. And just last week, we had just 8th edition of a RoboSoft in Switzerland with a record high number of attendees in the 2000, about 800 people. So this field has grown on very, very large, and I think this is the reason why the soft robotics is growing so far. And I think in soft robotics, the term is a very magic word in many ways that attract only people, especially interesting, important researchers come together because of the nature of soft robotics field. And if you just go to the next slide, you see a lot of events we organized in the past. We started 2012, we have a summer school, 2013, we have a conference, and then many associated events of soft robotics over years. And go to the next slide, we have even more online version of this event in Embodied Intelligence Conference in the last 5 years. And the growth of this community is because of the very interesting interesting concept of soft robotics attracting interesting researchers together for the very important discussions to discuss the future of this field of robotics. If you go to the next slide, you can see from my point of view, the soft robotics revolution is happening in the last 10 or 15 years, mainly because of the three main driving force, which is, robotics became cheaper, easier, and faster, and soft robotics only accelerate this direction of robotics research. So even without any skilled knowledge about mechanical design or mechanical fabrications, techniques, you can actually build robots very easily and quickly. And this was the main driving force of robotics. And I'm telling my Cambridge students that, if you're doing soft robotics, you're doing the right thing, because this is a very important research field and many people joining. But also, if you're not doing soft robotics yet, this is the field you can easily catch up for the beginners. And that's why I'm telling my students that everyone should be basically doing soft robotics. And please go to the next slide that shows why soft robotics is an important field. And this gives all different directions in robotics, from sensors to locomotion in air, on land, and on the water. And there are many different kind of important robotics applications, such as medical applications, locomotion applications, wearable applications, and industry, any other industry application. So this is not only for the application, but also the fundamental research, such as the simulation, modeling, control, and all the mechanical design and fabrication techniques. And those are the research fields that is currently expanding into this field of robotics. And what I wanted to highlight here is that this is just the beginning of this field, right? So I think this soft robotics is going farther and farther, and I hope this handbook of soft robotics can show you the depth and breadth of this field and contributing this community in the future, and contribute to the field to grow bigger and more productive. Okay, and with this, I'd like to start my presentation, and I'd like to congratulate you all again for the big milestones achieved for soft robotics community, and I hope you can enjoy this launching event in London. Thank you very much.
Brilliant. Thank you very much, Professor Ida. So if we could go to the next slide, please. Yeah. So at this stage, I'd like to invite the editor of the Handbook on Soft Robotics, Professor Thrishantha Nanayakkara.
Thank you. Thank you for coming. So it's an exciting journey. It took us about 2 years to do this. So finally, we are here. So in this book, there have been different, notions of softness, soft robotics in the field. So it was largely limited to rubber-like material, and that is soft, right? So, but we wanted to be, general, more go beyond that, and then have a broader definition or explanation for softness. So the softness is an emerging property for us. So in this, as far as this book is concerned. So, for example, on the left, you can see this Toji temple. This has survived 400 years of Japanese earthquakes, and it's a rigid structure, right? So, but when there's an earthquake, it can behave like a soft, like a snake. So it can exhibit autonomously, given some forces and their frequencies, intelligent behavior, right? So it is designed to be intelligent given forces of an earthquake. So it is rigid, but like it can exhibit softness given the forces. So it is our softness in this book is relative to the forces and their frequencies. So that also applies to rubber, right? So like human level forces and their frequencies, rubber is soft, right? But it is more general in this sense. So, and then this finger, robotic finger, developed by a PhD student, Parvati Sunilkumar. So for this finger to feel forces, it needs a nail, right? So it needs a nail, it needs a bone. So there can be hard structures within a soft, whatever the so-called soft structures, and they are needed to give this like emergence of embodied intelligence. It cannot be homogeneous, it cannot be radically soft. It can be soft and hard. It can be hybrid. Right? So that's we are relaxing this definition of soft robotics. So the central to the argument about embodied intelligence is this idea of ghost circuits. That is another term we are introducing in this book. Ghost circuits is a circuit that doesn't really exist, but it emerges when conditions are right. For example, this is a dead fish, and then George Lauder's lab at Harvard demonstrated that if there is a water stream, a turbulent water stream, there's an obstacle here, there's a turbulent water stream against it, it can start to swim like a live fish. So what that means is it has been evolved, the body shape and its stiffness distribution along the body has evolved to harness energy from the turbulent water, the vortexes, and then come into a harmonious circuit. So that means part of the circuit, dynamic circuit that is required to generate propulsion forces are in the water actually, right? And then the other part of the circuit is in the body. When they come together, they complete a circuit, a dynamic mechanical circuit. And then the function of that circuit is intelligent. It emerges an intelligent behavior. So we call it a ghost circuit because you cannot pick the fish and then see that. You cannot see it in the water. They come together and exhibit that behavior. And when, let's say, the fish swims in the stream, from point to point, the turbulence level keeps changing. And then in the live fish, what it can be doing is to regulate its stiffness to suit or stay linked to the circuit that is ever changing. So, but let's say if you put a ribbon here, it will flow down, or a stick here, it will flow down. That means this circuit is not a given thing, right? It can dissolve. So that is like, I call it a ghost, right? So that is important. So, but to maintain that kind of ghost circuits is, I believe, is the bedrock of embodied intelligence. Right? So embodied intelligence is not written somewhere, it emerges, and then it emerges through this kind of interactions, and then when the conditions are right, they come into being, and then when the conditions dissolve, they don't exist anymore. But to maintain these ghost circuits, biological counterparts do at least two things we have identified. So one is kinematic tuning. So I said the fish, when it swims through the stream of water, it has to regulate its stiffness. In fact, George Lauder's lab later found that there's optimal stiffness in the body that gives the best propulsion force. right? So that means the live fish should be regulating its stiffness to stay tuned to the stream of water. So I call it kinematic tuning. So kinematic tuning is the brain produces two types of commands to do intelligent behavior. One is, of course, these motor commands given to do motion and force control, like riding the bicycle. But in the background, it does kinematic tuning motor commands. I call it more MCT type commands, like motor commands to tune, motor commands for motion. Motor commands to tune are, for example, if it is bumpy, the brain would get the body to come off the seat and then ride the bicycle with bent knees. Why bent knees? Because the brain knows that in the knee joint there's an angle dependent damper. So there's when the knee joint rotates, the radius keeps changing, and that produces an angle dependent damper. What that means is by changing the angle of the knee joint, it can implement a low pass filter, right? So it's a damper that can be changed, and that means it can implement a low pass filter that filters out the bumpiness of the terrain, and then the brain can focus on low frequency information required to ride the bicycle, which is basically literally what it says is the head becomes stabilized and the knee joint does the work of filtering, right? And then the head can focus on model-based control and in a low-dimensional space. So the other application of kinematic tuning is perception. So when you go to a GP would, your primary care doctors would examine your abdomen by tuning the shape and then the shape and the stiffness of the fingers. Why do they do that? When they want to feel something, right? So the feeling is not also a given thing. You have to be coupled with as a gauge circuit. In this gauge circuit, the physician has to be dynamically coupled with the patient in a seamless manner for it to understand what the body random variables are. So it is not a given thing. You cannot just press and feel things. You have to do kinematic tuning to feel things, right? So it is perception and stability both. Kinematic tuning is important, and then that establishes these gauge circuits and maintains these gauge circuits. The other important thing we introduce in this book is behavioral lensing. Behavioral lensing is about taking MCM type commands in addition to MCT tuning commands actively to move around in various different ways to feel better, right? So they would do percussion, they would do bimanual examination, they would do unimanual examination. So in an equation, for the people who are from a mathematics background, what this means is the information gain, right? So because our sensors are part of the muscles, you can influence the sensors by actuating the muscles. For example, in a transfer entropy equation, so let's say you have you feel the internal body condition, let's say the edge of a liver, which is a random variable of d, and then that is a function that depends on your kinematic tuning parameters, right? And then behavioral parameters, which is like behavioral lensing parameter, that is like force control, motion control. And then let's say if you start with some kind of a default stiffness and default behavior of examination, and then move to a phi 0 to phi, which is a different way of examination, if you can reduce the noise in that distribution of the random variable from that dotted blue curve to the dark blue curve, we call it information gain, right? So we gained information subject to some constraints like pain reduction or time reduction, anything. So these three things are important: gauge circuits, kinematic tuning, and behavioral lensing, right? So then we'll go to
Handbook on soft robotics for engineers, for graduate students, so that they can find the principle we want to use in soft robotics. And specifically, Barbara and myself, we took care of the bio-inspiration part of it. So we tried to put some of the well-established models that we use in soft robotics, taken from nature, inspired by nature. So we give a sort of catalog of bio-inspired principles that can be used in engineering. We have some models even in mathematical terms in sometimes. So we hope this is very helpful for the engineers. And we select different models, biological models that can provide new insights in engineering. Animals, but even plants, so organisms that move in different environments, so that can crawl, so but they also fly or swim and penetrate also into the soil. And we try to identify and share the basic principles to then transfer to engineering. So of course it's not a copy, but it's really understand the basic principle insights that are very useful to improve the performance of the artificial system in terms of energy, of course, in terms of reduction the complexity of the control, for example. We try to give a little bit a different perspective. So, for example, we wanted to give models for movement, but we have, the traditional muscle-based kind of movements that we know very well. But we also have examples, as Barbara was saying, of movements without muscles, as it happens in plants. We also touched a little bit the sensory part with something on touch perception.
A video message from Professor Cecilia Lasky and Professor Barbara Mazzoli. And thank you very much, Trish, for your really insightful comments and discussion. So now we're going to hear from Professor Izuru Godege at Texas A&M. Professor, are you there?
Yes, David, can you hear me?
Yes, we can. Great. And we can see your slides too. So over to you.
All right, thank you. First of all, thank you to our editor, Dr. Nanayakkara, for leading this effort for 2 years and assembling a great set of researchers to put together this handbook of soft robotics, and it culminated in a very comprehensive overview of soft robotics that anybody can pick up and use in any part of their research. And it's great to see those in shelves. And now myself and Dr. Gilbert at LSU, Louisiana State University, was tasked to write the modeling chapter for this book. Now, as many of the researchers, Dr. Ida and Nanayakkara brought it up, soft robots, it's a relative term, but they generate locomotion by deformation. Now, for understanding this deformation, we need models. The other reason for the necessity of models is that the soft robots have a low threshold for deformation, given that it's low compliance, and they are very susceptible to deform passively when they are in contact, and they are applied some forces like touch. Now, for this, models can help anyone with cutting down the testing time, right? So if your model is very good, then you can do a lot of the testing virtually, save time. Or if your model is very efficient, you can use those in iterative design optimization. Now, there's this tug of war between the balance of accuracy and efficiency. Now, there's a new kid on the block, learning-based models. Instead of going through a classical approach, they're trying to gather data from a robot and then try to come up with the model that can predict and model the deformation. Now, good thing is that the learning-based models are very good at coming up with very nonlinear models that typically we overlook in classical approaches. Now, our chapter tries to give a good overview of all these. If you go to the next slide, please. Yes. So there are a few classes of these models. Now, the first one everybody came up with is the classical continuous curvature models. So they are based from continuum mechanics. Their approach is to try to model the whole robot as a unit with a few moving variables. Now, the lumped mass approach, on the other hand, try to break this down this continuum unit into smaller pieces, which can approximate the deformation by rigid unit. Now, the advantage of this is actually use the already established efficient algorithms, and the advantage of continuous curvature models is that if you found a good solution, closed-form solution, they actually perform much faster, like the Course-Right models for concentric tube robots. And hybrid robots, on the other hand, can try to strike a balance between the two, try to use both. The discrete Course-Right approach is an example where you break down a long piece of soft robot and individual segments are modeled as a continuum system, and then combining these would give you a sense of lumped system. Now, learning-based models, on the other hand, try to exploit the machine learning and the recent advancements in large language models, large multimodal models, to coming up with models to model a whole thing, the whole robot, or you can use it to compensate for non-linearities in the classical approaches. So we discuss both in all these things in the chapter. Now, next slide, please. So we ended the chapter by giving the reader some roadmap how to select the good model. Now, then again, this is actually kind of an art and a science, depending on how much experience you have. It used to be that it's a trial and error, or you inherited some model from somebody who worked on the problem previously, and then you just live with it. Now, what we try to do is try to come up with some set of parameters, and then you kind of identify which one you need from this model. For example, how accurate should it be? Or if you want to do a design of a robot, then of course you need that to be faster, so you can use machine learning and iterative processes. So the guidelines we came up with is, first you need to understand the robot, like what type of deformation does it have, how complex that is, how do they achieve the deformation, and how fast they are, right? And then obviously you need to look at the material properties. Are they stiffer or soft? Because if they are soft, then you need to account for all the environmental deformation aspect and whatnot, and what type of accuracy and precision you need, efficiency. And if you have a robot already, then there's a chance that you can get a lot of data, which could be used to come up with some machine learning models. And of course, finally, the needs for control, because if you try to do real-time control, then we'd like to have a real-time, that means a faster model. Now, if you consider all these, then we have included some tables where you can use, then would lead you to the type of model that you need. So I hope people will find this chapter useful. And over to you. Thank you for the opportunity.
Great. Thank you very much, Professor Godege. Really interesting. So now we're going to move to Professor Ian Walker at Clemson University.
Hello,
Can you hear us?
Can you hear me?
Great, yes.
Okay, great, thanks. So I'm now with the University of Wyoming, but this work was done at Clemson University. And so again, my co-author Manu and I, we're honored to be part of this group. It's a very distinguished group with lots of really interesting ideas. Our chapter sort of starts to address the idea of some of the challenges when you want to take soft robots and apply them to particular applications. So in terms of the problems that you encounter by trying to solve particular application-related problems, and then some of the back to the modeling issues that Isuru just spoke about. So our particular application is in the construction industry, where our goal for the project we were working on was to improve the delivery of cement. So to be able to give higher fidelity structures, to be able to essentially 3D print cement in a robotic sense. So our basic idea, and the top left gives the general idea of it, was to take the industrial cement hose and robotize it. So in contrast to, I think, a number of things that we're going to see today and are talked about in the book, rather than sort of building a robot from scratch, what we did was we inherited the state-of-the-art, the industrial robot hose, and you can see one moving in the video here. And so the goal was that we would be able to make this move essentially like a snake. And so we put tendons down the outside of it, you can see them in the video, and then by essentially applying tension to the tendons, we're able to change the shape of the hose with the idea that we would be able to print high fidelity things in concrete. So we started out, things worked out quite well, and you can see we're 3D printing of our very first experiment down on the left, the bottom of the slide there. And that what was printed there was supposed to be a cylinder. And I think at a quick glance, we can all see that it's not a cylinder and not even close to being a cylinder. And so we scratched our heads. We were using some of the models that Isiragodiga just mentioned a little bit before. And so for a while, we were kind of puzzled as to what the story was. And so the bottom line in this particular case is that the robot, the hose, was soft in ways which were not helpful. In particular, what we were not expecting is that the hose compressed under the strains we were putting on it with the tendons, that the hose was compressing. And so you can see the point of the video on the right is that you can see a little red ball at the bottom. And so that is just strung through the center of the hose. And so it has constant length. And as we start rotating the hose around, you can see that the ball is extending and contracting from the hose, indicating, illustrating that the hose length is actually contracting. Okay, well, there are models, some of the ones that, again, were just spoken about, that take into account contraction of a section, so making basically a long soft robot a bit shorter or a bit longer. But we couldn't really use those practically in this application because we didn't have control over that. That we don't have direct control over how the hose is compressing in the axial sense. So we had to scratch our heads a little bit. And so if we can go to the next slide, please. Thanks. The basic problem was that the models we were using were based only on geometry, and they weren't taking into account the tensions and the forces being applied to the system. So essentially what we describe in the chapter is going back towards the chapter that Isuru just mentioned, going back to modeling. And so we developed a way of compensating for the actual compression by basically looking at the statics models and looking at the mechanics of the situation, understanding a little bit more about what's going on. And then we were able to come up with some models, in particular, some models that did not require us to know the tensions in the cables, because that's something that would have been practically more of a problem to adjust. So basically, we came up with a new elasticity compensation model that basically let us figure out how much we should pull in the tendons and compensate for the compression that was happening. So intuitively, the way I like to think about it, probably because I don't ride horses, is that if you imagine you're riding a horse, as you have reins, you can loosen or you can tighten the reins. And there's some point at which, you know, if you give the horse too much rein, then it can do more or less what it wants. And then if you pull in a certain amount, then you can really restrain the horse. And there's sort of a magic moment in there, a magic spot that corresponds to preload in tendon-based devices. So basically what the model displays, and the details are given in the paper, is basically how much to pull in on the tendons so that you have just enough preload, just enough tension, so that your robot, as you move it around, does not change its length. And the net result of that was illustrated in the picture at the bottom right. And so here is the net results. Still not perfect. There's a lot of things to be taken into account when you're trying to model and control soft robot systems, but it got a lot closer. And so I hope that anybody interested, if they read the chapter, will get a sense of some of the issues you have to go through when you're trying to apply a soft robot to a particular practical situation. And there I'll stop, and again, thank everyone for joining.
Great. Thank you very much, Professor Walker, and a really nice continuation from the previous chapter as well. So now I'd like to invite Professor Shinichi Hirai from Ritsumeikan University. Professor Hirai, are you there?
Yeah.
Great, so over to
Can
you.
you hear me? Okay, thank you. Okay, in this chapter, I focused on soft robotic hands, performing object grasping and manipulation. So soft robotic hands include soft materials or soft structures over contact region with the grasped object. So this softness is very, very effective for adaptability against uncertainties in real world, especially in contacting the operations. But first, I've classified such soft robotic hand into 6 categories. I'm showing here. So the soft pad hands, suction hands, jamming hands, bending finger hands, expanding membrane hands, and remotely deformed hands. Based on the driving the strategies. Okay, also they introduced mechanical models of several the hands. Here in this chapter, I emphasized the embodied intelligence. Okay, the Thresh introduced before, in soft robotic hand. Also, that is how in this chapter, I showed how softness contributed to stability in the object grasping and manipulation. Okay, the next slide, please. Okay, the one good application of soft robotic hands would be food manipulation. I've introduced several soft robotic hands designed for food manipulation. As shown here, and also I've introduced soft sensors applied to soft robotic hands, including resistive, capacitive, and magnetic sensors. I then introduced entropy reduction in soft tactile sensing and material design for phone sensing. It means that we can such soft material can perform the information processing, and also we can if you design material property, we can improve such kind of the information processing capability. Okay, that's it. I hope you get interesting this chapter. Thank you very much.
Great, thank you very much, Professor Hirai. It's really interesting. So now we'll move to Dr. Angus Clark here in the room.
Hello, yes, excellent. Brilliant, good afternoon everyone. Hello to everyone online. I want to echo the other authors as well so far. Massive thank you very much to Professor Nanayakkara for the incredible amount of work that's gone towards this handbook. Now the chapter I'm going to talk about is on malleable robotics. So myself and the authors, Alex, who's with us here today, and Dr. Nicholas Rojas, who's online as well, and Shimran Wang, is about a new type of serial robot manipulator, so a type of robot arm. And most robot arms are 6 degrees of freedom, or 5 or 6 degrees of freedom, sometimes even more. And this makes them expensive. And this is one of the key things that we tried to address here. And how do we address it? Well, through soft robotics. So malleable robots go away from this tradition of high degree of freedom serial arms and go to low degree of freedom. Now, normally, that would impose limitations on their workspace and their capability. But by introducing a component called a malleable link, a part of the robot that is capable of changing, it can become both soft and rigid at the flick of a button. This means that despite having a low degree of freedom in the joints, the robot can actually achieve a significantly more complex workspace. Now, what we present in this chapter is, in the first half, which is what you can kind of see on this slide, is the fundamentals of prototyping. It's really going into depth and hopefully is a very valuable resource to people who want to replicate this technology of variable stiffness structures, specifically layer jamming, and goes from the structure itself in the top left, where you see kind of layer jamming, as well as the supporting structure inside of this, which is a spine and some of the modeling behind that, how that can be made into a link, and then how the link can be multiplied with joints to create a robot arm. Now, if we go to the next slide for me, thank you. We don't just stop there. The next stage of this is you now have a robot arm, but it changes. And this makes it really difficult to model this and actually control this robot arm. The traditional ways of doing this, DH parameters or screw theory, don't really work without integrating lots of complex sensors. So one of the things that we also propose in this chapter is a new method using distance geometry, specifically using Cayley-Monger determinants, which is the kind of triangles at the middle top. And then we also model some of the internal structures using kind of your traditional Kosterap modeling. From that, we can generate inverse and forward kinematics. And this allows us to predict what's actually, what has this robot, what is this robot capable of, which you can kind of see from the different workspaces. So one of the things I want to highlight here from this image in the bottom right, this is a 2 degree of freedom robot arm. It's incredibly simple. And yet some of these workspaces that you're seeing here would be achieved by a significantly more complex robot, a 3 or 4 degree freedom robot arm. So anyone who's familiar with robotics will know that one of the most expensive components, in fact, the most expensive component in a robot is its joints. By cutting those down, you save in cost. And the final part of this chapter that we explore is how we actually interact with these robots. If you've got a structure that is changeable, you need to be able to predict what those changes are actually doing. One of the things that we explore with this is through the use of holograms and human-robot interaction, which allows us to see in real time the changes that you're making and how those affect the capability of the robot. So I hope this chapter will be a very valuable resource for anyone reading it.
Fantastic. Thank you very much, Angus. So now we're going to transition to Professor Christian Duriez at INRIA. Are you there, Professor?
Yeah, hello?
Great, yes, we can hear you. So over to you.
Okay. So thank you very much for the invitation. Actually, thank you, Trish, for asking me to write this chapter. So initially, when Trish asked me, it was to write a chapter about FEM, a finite element model for soft robots. But in reality, for me, what is important in the modeling of soft robots is the computation and the use of mechanical compliance. So in this chapter, I show how this mechanical compliance can be computed and used, in particular by using FEM computed in real time. So the content of the chapter is first, the motivation, why we want to use mechanical compliance, and how we can compute that to notion of continuum mechanics and finite element modeling. Then we derived the quasi-static and the dynamic deformable motion. And through Lagrangian, we show that we can compute this compliance. Then we will show, I demonstrate how we can also effectively model actuators, also the concept of effector. And at the end, I show that how we compute the inverse static and inverse kinematics. But most importantly, and that's why also I show it on the image, we develop an algorithm for computing the inverse kinematics of a soft robot, which is quite generic, but it's also compatible with contact, and in particular when you are able to model the contact with an obstacle. So I included this image because I think it's essential for me to model the contact when you are modeling soft robot, because all the purpose of this soft robot is to go into and interact with their environment. So I don't have all the time for all the detail about the modeling aspect, but I think we can go to the slide. Just a motivation, and I start with that chapter. So why I do the emphasis on compliance, and to give you an idea of what the chapter is about. I start by explaining the concept using an analogy with the problem of equivalent springs that all of you knows. So the springs in parallel and the spring in series. So these soft robots, theoretically, they have an infinite number of degrees of freedom. In practice, we won't be able to manage all these degrees of freedom. So we want to use a reduced number anyway, a reduced number of degrees of freedom in our method, so in our modeling methods. So, and when we compute an equivalent springs, so we have springs in parallel and springs in series, but when we are in parallel, what we do in practice is that all the springs that are in parallel, we say that they have in fact, they have a limited number of degrees of freedom. They can only move all together. So we do a DOF reduction, and that's the stiffness approach. So when you go from a reduced number of degrees of freedom, you are in fact adding springs. So this is something that we will use in our methodology to, for instance, to reduce the number of degrees of freedom and to accelerate probably the computation of the methods. But we can also do the same thing. We can also use a reduced number of degrees of freedom by this this DOF equivalent DOF of the equivalent springs in series, and in that case. You all know that to compute the equivalent springs when we have springs in series is to use the inverse of the stiffness, which is the mechanical compliance. And in fact, when we do that, we do not do a DOF reduction. We do a DOF selection. We select in the structure the degrees of freedom that are interesting. And it's particularly useful when you don't want to reduce too much the size of your model. In particular, when you have contact, you don't want to reduce too much your degrees of freedom. So it's so that's why, in fact, I push this notion of compliance, mechanical compliance. Then you can go to the next slide, and then starting with trying to convince you that we need to compute this robot compliance in the chapter. I explained that to obtain it concretely, we have to go through continuum mechanics and develop numerical methods like FEM to get, in fact, this compliance. But in fact, we want to have this compliance in certain space. So we'll use the Lagrangian formulation in order to develop, for instance, an actuator models thanks to the Lagrangian formulation, and be able to compute basically the compliance in actuator space, in contact space. So there is also contact with the environment to compute the compliance in effector space, and how we can couple. So this compliance, we'll see that it couples the effector actuator space. And out of that, which I show that we can derive basically a very generic model for direct and inverse kinematics, and there is also some extension for sensor model. So that's all the spirit of this chapter, and that's it for me. I hope you will enjoy the chapter by reading it.
Brilliant. Thank you very much, Professor Duriez. And finally, I'd like to invite Professor Jamie Pike from EPFL to present. Professor Pike, are you with us? Can you hear us, Professor Pike?
I was looking for my microphone button. Hello, everyone. I thought you were presenting for 2 slides and 2 minutes, but I guess I'll try to, I'm not so sure how you're doing the time, so I will just stop when I get stopped. But hello, everyone. It's unfortunate I don't get to see everyone's face except for my own slides, but I was very happy to be invited to join this this effort in creating the first handbook for soft robotics. So this origami robot chapter is written with Professor Cynthia Song from the University of Pennsylvania in Grasp Lab. And we start by defining what is really a softness. Are we really trying to only achieve robotic movements and robotic understanding robotics through softness in materials? Not necessarily, I think. So I explain why origami robots should be considered to be part of the major stream of soft robotics, not just because it only has a chapter in it, but because this is quite important. Any robotic system is only as robust and as strong and as more intelligent and precise as its weakest link. So if whole thing is just softness, a glob of softness, you may be addressing the soft materials aspect of it, where the sensors and actuators can take advantage of the intrinsic softness. It does not necessarily mean you're addressing the rest of the system, where you're looking at soft control methods, what Professor Diaz just mentioned, how to control this multiple aspects of soft materials and how you're able to predict their movement, but also be able to control them as well. So where origami comes in is where we can endow multiples of degrees of freedom through its kinematic relation with the surroundings. By convenience, origami is a paper art, so where the final shape of your structure is defined by the number of folds, the position of folds, and the sequence of folds that are produced. So in this chapter, we talk about how, can I go to the next slide, please? How multiple different formats of fold creates its own transmission. So depending on where you put in the input and whatever the output side is, the end effector is, you're able to get a predefined trajectory as well as a transmission ratio. So you're effectively changing the force vector of input to the output. So Professor Song and I really goes through on how these transmissions can be modeled and applied to origami robot system that's either independently, completely on its own, a full robotic system, but also combined with soft materials, intrinsic softness, we're able to create at the end a soft and fluid motion. So if you go to the next slide. On the chapter, we talk about different aspects of origami robotics. The modeling, where Professor Song highlights a lot of design, control, and manufacturing. And it gets really exciting for, I think, for the rest of the soft robotics community that I've observed. The reason is, by definition, origami robots are quasi-2D. Things are inherently embeddable. So how you would design your sensors and actuators, they would be manufactured in quasi-2D manner. And what's great about that is that you're able to embed these essential robotic components, meaning sensors, actuators, microcontrollers, transmission, within your either soft structure or existing platforms as an addition. So we go into a bit of how these are manufactured and could potentially be integrated for different applications. And we touch base on whether the materials and design algorithms that we can employ to bring this to your future research. And that would sort of summarize our chapter. Thanks for your attention.
Okay, fantastic. Thank you, Professor Pike, and thank you very much to all our authors for those really interesting presentations and observations. So at this stage, we can move to the discussion with the authors and audience Q&A. So for those who would like to contribute or to ask a question, I'd ask you to please raise your hand. And if you're asking a question, if you can say your name as well, that would be great. Or if you're joining us online, you can post a comment on the YouTube live stream. So to allow people a few moments to think of questions and think of thoughts, I might kickstart the discussion, and I might call on Professor Pike to talk maybe a little bit more about, I know origami robots use a lot of straight crease design, and I'm wondering how can curved creases unlock new opportunities, please?
A great question. Did you prepare that?
Maybe.
I think one of the drawings or the figures that we prepared actually shows the curved crease. Personally, I haven't worked with a curved crease per se, but we have a work on the kirigami pattern that allows us to create a metamaterial of the origami structure. What does that mean? Like I just briefly mentioned, any origami is only as strong as its least, the weakest link. So instead of going directly to the curved crease that is very difficult to control the manufacturing and the end effectors positions, we create the raised kirigami patterns allows us to have much a thicker surface that gives effectively another, literally a quasi 2D, 2.5D raised surfaces that would create much thicker and robust links. Curved creases create obviously different format, but for the movements, we don't currently see any more additional benefits. It will have a benefit if you're talking about final transformation of shape, but in terms of the functionality of the movement, currently with all plethora of crease patterns, we have more than enough to deal with for the moment.
Okay, great. Thank you very much. Now I might ask Dr. Angus Clark a question. He's here with us in the room. So I really like your, and I know Alex Ran is with us too, and Nicholas Rojas is online. I really like the tutorials you provide in your chapter on malleable robots. So my question is, how can malleable robots close the technological gap that separates current cobots or collaborative robots from achieving accessible and flexible manufacturing automation?
That's a great question. One of the big differences with cobots is their human-robot interaction. So you've got robots that are in a very different environment to what we would expect industrial robots to be, where they would normally be locked behind cages, performing very rapid tasks. Cobots, the difference is you have them working alongside humans, working together to try and complete tasks that are potentially more complex, more changing. So with a normal robot, you program it, you let it do its task. They're brilliant at doing that many, many times over. With a cobot, the idea is that you can kind of move away from that area of thinking and use the benefits that a robot can provide, which is repeatability, its precision, its accuracy, whereas with a human, they have that kind of, I can use the word malleability, where they can kind of adapt to problems. So a good example is in car factories, where you've got assembly stations where people are typically bolting parts together. You could do that with a robot, but that requires everything to be exactly aligned in exactly the right place. If you combine that with a human and a cobot, you can actually have a bit more flexibility in that assembly line, makes things much cheaper, makes things much more adaptable should you need to make changes. Where malleable robots come into that is that human-robot interaction. It's not an option with malleable robots, it's a requirement into how they work, which is just a very different way of thinking, but should be quite interesting going forwards.
Yes, absolutely, really interesting. I think it'll unlock a lot of boundaries. So yeah, it's great. Thank you. Do we have any questions or comments in the room? Yes, we got a microphone to you. Thank you, Rosemary.
Hi, I had a question on the chapter by, I don't want to butcher it, but Ian Walker and Manu Srivastava on the cement 3D printer thingy. So from what you've seen and thought of about the whole system, what do you think the most promising application could be in the future? Because it looked quite exciting.
So unfortunately, Ian Walker had another commitment. So Thrish, are you able to comment on this? Or maybe Asuro Godage, potentially?
There? Is Manu there?
No, I don't think Manu is there. I don't see.
Okay, it's fine. Isru, you want
Yes.
to take
Yeah. So your question is about this continuum and soft robots for construction. Is that correct?
Yeah.
Okay. So your question is other application that large-scale continuum robots can be applied.
Yeah, basically.
Yes. So, I mean, you can consider large-scale structure painting, right? So that's one application. The problem is, though, as you can see, the concrete is very heavy, right? And the soft robots that we have, they generate motion by deformation. That means it has to have some sort of a flexibility. And the weight and extra forces applied on these structures is not really working together, right? And then we need to find ways that how to make them work together, like strike a balance between the two. Now, if you are considering an application like painting, then that is more feasible, right? You can build larger and longer, flexible snake-like robots that can paint an entire building without any issues. So application-wise, yes, we are exploring now the practical side of these robots in areas like construction, right? And we ourselves are also kind of looking into one not so long soft robot, but a mobile system-mounted robots for printing structures, where they can help individuals with natural disasters, things like that. Yes. Another application would be doing search and rescue in buildings, right? Where you don't necessarily have a payload. Instead of sending cameras, you can send one or a long one robot along openings like ductwork and things like that for looking for survivors. So these are active researchers explored by different researchers around the world. Did that answer your question?
Yeah, thank you.
Yes, thank you very much. Okay, great. Do we have any other questions or comments in the room? We have one up here.
Thank you. Fascinating. Alec Robertson, Design Education Trust. I'm really coming from the kinetic viewpoint of arts and design, and many of the things I've heard today are obviously going to contribute to making soft movement in consumer products where you can add value. And my question, I suppose, is there are people who deal with soft movement. They're called dancers and choreographers. Is there any kind of influence of that field towards within your research?
Trish, do you want to take that, maybe?
Yes. About 10 years ago, I did a human robot dance in collaboration with the Dance Institute. So the title was Trespass. If you search for Trespass, you should see that on YouTube. So the idea is how can the human enter into a robot space and then understand the robot, its negative spaces, and how to coexist with the robot in a negative space. So that we showed that through a dance. And then there were various narratives about it. Like, so it is about, when somebody goes to a new country, how they try to fit into the new culture, and then things like that. So it is a robot and a dance to two species trying to coexist in a shared space. So this kind of artistic depictions are going to come through soft robots because it's inherently safe to deal with them. And then like Jamie showed, like origami structures are really artistic. And then then Angus is like, this kind of malleable robots, right? So you can have just 2 motors but do various workspaces just by changing these links in different ways. So that is artistic, right? Yeah. Did that answer your question?
Yes, yeah, in a sense that the experiments with choreographers and dance and movement, because ultimately trying to create soft movement, and all the technology behind it is what your book's about. But ultimately, that's the goal, isn't it? Soft movement.
That is exactly. So the dead fish I showed you, it's a soft movement. It's a dance with the turbulent water. So it is like a stream against you, but like you dance with it. You just move forward with it. It's artistic.
Thank you.
Great, thank you. So we have a number of questions and comments coming in online as well, one of which is from Amir Tafrishi, who says, very interesting talk. Could the introduced ghost circuits be viewed as a form of under-actuation in passive systems?
Yes, you need to have redundant degrees of freedom, just like that dead fish, to harness the network in the environment. So the essential thing about ghost circuits is you as a small piece in a network dynamic system is going to influence the entire network's dynamics to work in favor of you, your favor, right? So that small fish is not fighting against that massive stream of water. It is just harnessing it for its own advantage by just creating these vortexes around it, right? So that is, you need a little bit of passive degrees of freedom, and then you need actuation, you need external movement and internal regulation, stiffness regulation. So it is not just having under-actuation.
Great, thank you. Do we have any other questions or comments in the room? Yes, we have one up here.
Hello. Thank you very much for the presentation and the knowledge you're outputting through this handbook. I have a question for Professor Duriez on his chapter for the mechanical compliance. And more specifically, I was wondering whether the fluid structure interaction element was considered into the modeling and whether that is discussed or was it left out? Thank you.
Thank you for your question. So we do have we do provide a model for fluidic actuator, which are based on the fact that you assume that you have pressure in different cavities where you have if you have different actuators, and basically so it's a kind of we assume that the behavior of the fluid is in quasi. So basically, there is no dynamic in the fluid, but we do provide modeling for static, I would say, behavior of the fluid. So it allows already to compute, for instance, inverse statics of compliant soft robots using soft actuator. Of course, the assumption is that you do perform like a kind of slow motions, and not very, very fast motion of fluid inside the robot. But it's already a beginning. Of course, for having more complex fluid structure interaction, we would need to add model of fluids, and that would require much more computation. It's possible, but maybe not in real time.
Great, thank you. So maybe an open question to the authors. What do you envisage as the biggest challenge in soft robotics right now?
I think I can answer that one. I'd be interested to see if people agree with me. I'll just speak loudly.
Oh, yeah.
Reliability would probably be the biggest challenge. We're good at making robots, we're good at simulating robots, we're good at kind of predicting what they'll do, but actually robots in general, what people expect from robots is reliability. It's that repeatability, and actually I think the best demonstration of that was with Professor Ian Walker's work, showing that something that we might perceive as simple as drawing a circle is so complex because you can do all the simulation and modeling that you want, but actually having it follow through and controlling all of those variables is the biggest challenge, although I would love to hear from the other authors to see what they think.
Yeah, do any of the other authors have any thoughts on this?
I can try, but I think it will be in the same, a little bit the same, but maybe in other words. I think for me it's more to go from prototype to something more advanced, in particular to also find applications where these robots are really useful. In particular, I think we all know that soft robotics is particularly useful in soft robotics, in surgical applications, and but I think there are other aspects of where soft robots can be useful, and also I think we also should look at more hybrid soft and rigid robots. There are a lot of applications, I think, for that. But today it's more we are very good at as a community as providing new concepts. But we need to go from this concept to something more applied, I would say. So it's a big change.
Great, thank you. Okay, and thanks to Carolina Silva and Rashmi Wejansun-Dara for those questions. We're almost out of time, or maybe are out of time already. Are there any final questions or comments from the room? And if not, I might pose a question to Thrish and our authors. What does the future of soft robotics look like?
The future depends on you. So the future researchers, our community is a very bottom-up community. We have to respond to global needs. It can be disaster response, it can be surgery, medical training, it can be agriculture, sustainable agriculture, more productive or precision agriculture. It can be underwater resource harvesting. There are numerous applications, right? So our community right now they are addressing what they are passionate about. It's up to you. The community, pick something and then serve a global problem and solve it. And then, it's all about humanity. And there's nothing called a direction. It has to be driven by the community. So I would say that's.
Yeah, great, thank you. Do any of the other authors have any comments or thoughts on that?
Jamie, do you have anything to say?
Oh, well, I congratulate everyone for getting this through, and biggest congratulations and respect to Trish for being first of all, recruitment and follow through and putting all those chapters together and just making it happen. And I think us celebrating the 25th anniversary of embodied intelligence was really perfect timing. So again, Trish, thanks for not finishing this too early either, because I think this is a really good opportunity to really mark the 25th anniversary of how the soft robotics community all came together. And I think the question was, what's up for future? Well, I was hoping for the second edition and third editions to come, and eventually it becomes a handbook for anyone who wants to study robotics. So that's my small hope.
Great, thank you.
Great, yeah. I think that's a really nice note to end things on. I know there are more questions in the room and more questions online, but hopefully we can continue these discussions. Yeah. Thank you very much to Thrish and to all our authors for the really insightful overview and discussion. Thank you to our audience, both in person and online, for the really interesting comments and observations. Thanks to the events team, the AV support, and the catering team who've helped us host this event. And finally, the Handbook of Soft Robotics is available online and in print from Springer Nature and across a range of bookstores. And we hope that you will join us now to continue our discussion over some refreshments outside the lecture theatre. Thank you all very much.
Thank you.
Thank you.